Hi, my name's Kerry Troy. I'm going to talk to you today about the conservation of linear momentum applied to control volume problems. The basic problem that we have that we'll work on today is one that looks like this, where we have some inflows and outflows to a control volume. This could be a section of a pipe, and we're given something about the fluid properties, things like the density and the specific weight. We might know the flow properties, so that would be the pressures, the velocities, and the flow rates at the different cross sections. And those would either be given to us directly or things that we would figure out using Bernoulli's equation or the pipe flow energy equation or conservation of mass. We know something about the control volume, so that would include the areas of the different cross sections that we're evaluating, the weight of the entire cross section and the fluid, and any angles involved in the problem. And what we're trying to figure out here are the two forces that are required to hold this control volume in place. And the force is a vector, so there's two components, one in the x and the z. And we need to figure out what the magnitude of those components are. And we're not going to talk about, what is that force, where it's coming from, but, it could be coming from the internal force related to things like the flanges, or there could be another structure holding it in place. So if you want to do this problem with numbers, there's some numbers given to you on this slide here. To get the most out of this video, I would recommend pausing the video now and actually trying this problem. And ideally you would get stuck, and that's where the rest of the video would come in really helpful. At the end of the video, I'll give you the answer to this problem for these numbers. But now I'm going to walk you through how to solve it. So I like to start with the forces on the control volume. There's sort of a usual set of forces that we consider for these problems. One important thing about all of these problems is putting in a coordinate system. So I've got one up here on the upper left with x positive toward the right and z positive upwards. That's sort of a good first step for all of these problems. We're going to think about the weight. So the weight includes the control volume and the fluid inside. And obviously that's going to be acting in the downward direction. So I'll add those in as forces there. The other forces that we include on these control volumes typically for these pipe problems are the pressure. And the pressure is a little bit tricky, but I'll walk you through it here. So the pressure force that we're considering here is the pressure force from the fluid outside of the control volume acting back in on the control volume. And for this face that I'm highlighting here, that force would be in this direction toward the right, because the fluid outside of the control volume is pushing back on the fluid inside of the control volume. And the same would be true actually right here, and also right here if this was pressurized, but it's a free jet, so we have no pressure. We'll work in gauge pressures, so that pressure will go away. Anywhere you have fluid that is sort of cut for your control volume, which would be here and here, basically things we call the control surfaces, where fluid is fluxing in and out of the control volume, that's where you would have to consider this force. And again, no pressure at free jets if we're working in gauge pressures, which we generally do for these kinds of problems. So if you want to write those in, for the number one cross section here, we would have a force that would be P1A1. We're not going to worry too much about any sort of hydrostatic pressure variation in the fluid, because generally speaking with pipe flow problems, the fluid is pressurized by an amount that's pretty large relative to any hydrostatic variation. So you could think about this P1 as sort of the average pressure across the cross section. Anyway, multiplied by the area, P1A1 would be the magnitude of that force. Section 2, P2A2, so notice it's acting back in on the control volume. That's the key with the pressure force. And I'm going to go ahead and write in a P3A3 up there. Obviously the P3 is 0, but sometimes you have to deal with that. And for the pressure, you would actually need to break that into the vector components in the x and z. So another force that comes into play is the support force. So the support force is actually what we're thinking about and what we're trying to figure out. Again, it's whatever is holding the control volume in place. We're not going to get into what that would be for this problem. And again, it's a vector, so there's components in the x and the z and potentially in the y direction if this is a three-dimensional problem. You may not know which direction that force is going to act, so you can just assume it to be acting in one direction. I think it's easiest to assume the x component is acting in the positive x, and similarly with the z. And if you get a negative number, then you know that you guessed wrong and it's actually going in the other direction. But I usually just assume it's in the positive x and z directions. Sketching those in on the control volume would look something like this. And again, the pressure, number 3, would be acting back in on the control volume there. So in summary, we have 3 forces: weight, pressure, and support forces. If we want to go ahead and write those down, I like to write them in terms of the different components. So in the x direction, we have the pressure force at number 1. At the 3 cross section, that would be actually a negative P3A3 cosine times 40. And we have that x support force acting in the x direction. In the z, with z positive upward as we have for our coordinate system here, we have a negative weight of the control volume, negative weight of the fluid. We have a P2A2, that's a positive P2A2 because it's the pressure from the fluid outside of the control volume acting back in on the fluid inside the control volume. Similarly, with the number 3 cross section, we would have a negative P3A3 sine 40. That's the vertical component of that P3A3 force. And then we're assuming this TZ is going to be a positive in the upward direction. So that's this one here. Again, the P3 would go away if we have a free jet, but I left it in there because sometimes you do have a pressurized section that involves some angles, so that's how you would do those. All right, so those were the forces, and now we're going to deal with the so-called momentum fluxes. And anywhere you have fluid entering or exiting the control volume, you will have to deal with these fluxes, okay? Those are called control sections. They are fluxes of not only x momentum, but z momentum. So it's actually a vector, so the same way we did the forces in the x and z, you have to do the fluxes in the x and z as well. They look like this. So in the x direction, you have the density of the fluid times the component of velocity in the x direction times the flow rate for a given cross-section. You'll have one of these terms for every single cross-section. I'll talk about the plus or minus signs in a second. And the same is true for the z, except that for the velocity, you're considering the vertical component of the velocity at that cross-section. The key for this, the fluxes, is really to get the signs correct. So how do we do that? Well, here are the fluxes in the x and the z, and here's how you do the signs. So basically, the velocity in the flux terms is going to get a positive or negative sign depending on whether that velocity component is positive or negative relative to your coordinate system, okay? So for example, if you had a velocity at a given cross-section that was in the positive x direction, you would get a plus sign here, and if not, you'd get a negative sign there, okay? The flow rate term actually is very easy in terms of the signs that go in front of it. You're going to have a positive sign for an outflow and a negative for an inflow, okay? So let's just do this. It's the easiest way to figure out how to do this. Okay, so I'm going to make a chart again here with columns for the fluxes in the x direction and the z direction, and those would be the x and the z as I've got here. So let's do the cross-section number 1. So all of the action in this case is in the x direction. There's no vertical component of velocity, so the fluxes that you get rho. We get a positive v1 because this velocity is actually in the positive x direction, and then we have a negative q1 because this is an inflow into our cross-section. There's no vertical component of velocity or momentum at that section, so we don't put anything in for z. Similarly, for number 2, all of the action is in the vertical direction, so we have nothing in the horizontal. We have a density times a negative v2. It's negative because that is the component of velocity in the vertical direction, and according to our coordinate system, that is in the negative z direction. It's an outflow, so we have a positive q2. For cross-section 3, even though the pressure is 0, the flux is definitely not 0 there. And if you do the signs correctly for that, it should look like that. So the x component of velocity is in the positive x direction, so that gets a positive sign. And also the z component of velocity is in the vertical direction. So you can break this velocity into the 2 components of the vector and then just multiply by the flow rate and the density. So that's how you do the fluxes, and I like to do them in terms of this chart here. So the last step for these problems is we're going to gather all of the forces that we calculated or sort of tabulated, and we're going to set them equal to all of the fluxes. And we're not going to just add every single term that we did for this method. The problem is that momentum and forces are actually a vector. So we're going to do it separately for the x and the z directions. Okay, so The equations that we're going to end up plugging things into, there's actually two equations, one equation for each component of our coordinate system, x and z. We're going to add up all the forces in the x direction, and we're going to set it equal to all of the fluxes in the x direction, and we're going to do the same for the z. Okay, so watch how this works. So I think it's best to make a table. So I make forces on the left and fluxes on the right. We have our x and z components for each. And now all we're going to do is populate the table with all of the different forces and fluxes that we dealt with before. So in the x direction, we have all of these. These are the same ones we had before. In the z direction, we have all of these. We're careful to keep all of our signs correct. The fluxes is the chart that we just did, where we had those two fluxes for the control volume section, control section number 3. And we're keeping everything straight in terms of x and z. Now the last step for this method is we are going to gather all of the x forces, we're going to add those all up and set them equal to the sum of all of the x fluxes, okay? So I'm going to add the x down, and then there's going to be an equal sign between the forces and the fluxes. So for the x, it looks like this, okay? So we've taken all of these three terms, we've put them over here on the left side of the equation. For the fluxes, we've taken these three terms, they're over here. And now we would solve for whatever we're looking for if we could get it from the x alone. And actually that would give us the x component of that support force if we plug everything in. For the vertical force, same thing. So we're going to take all of the forces here, we're going to add all those up, and we're going to set them equal to the sum of all of the fluxes in the z direction. So we have another equation for z, looks like that. A little bit messy, but I think you know where it all came from, so it's nothing too surprising. And again, depending on what is known or unknown, you can solve for different things. In our problem, we don't know the support force, so we can back that out if we plug everything else in. Other problems, maybe you're solving for a pressure, maybe you're solving for a weight or whatever. Okay, just depends on the particular architecture of the problem. Again, the pressures at the control section number 3 for this problem, it's a free jet, so those go away, but I did want you to include them in there to see how they go, okay? All right, so the big reveal. So we have this problem, this is the one with numbers, so you have different flow rates and areas and pressures. And the question is, what's the actual support force required? So are you ready? The big reveal, here we go, with some amazing graphics. Bam. Okay, so if you did the problem correctly, you should get a value of negative 154 newtons for the support force in the x. Remember that we assumed that was acting in the positive x direction, so the negative sign actually just means it's in the negative x direction. And then similarly, the z support force, 95 newtons, that's a positive value, which means that it's in the same sign that we assumed, which is positive in the upward direction. So that's basically it.